So this is a picture of the orbit of Mercury, okay, on the left, and it's the sun is right here, okay. The Earth is the blue dot, okay, and the center is just the center of this ellipse, okay. It says the sun is located at the focus of an ellipse. There's nothing physical located at the center of the black dot, or the other focus, the blue dot. Oh, I'm sorry, my bad. These are the foci. I thought it was the Earth, my bad. But here's the orbit of Mercury. Like, it looks circular, but it's actually an ellipse, and the sun is slightly off-center, okay? Here's another picture. This is of Halley's Comet. So you've got Halley's Comet right here. It moves on this elliptical path, right? And the crazy thing about Halley's Comet is that it has a extremely elongated ellipse, okay? The sun is at the focus of the ellipse. We'll talk more about what that is in a second. It almost looks like, though, that it's like right on the edge. And that's because Halley's Comet comes extremely close to the sun, it grazes by the sun, and then it goes back out around, and it goes really far away, actually. Like, how far away does Halley's Comet go? I don't know. We'll be able to... I can tell you that it takes Halley's Comet something like 80 years to take its trip around the sun. We're going to use that number 80 in a little bit to figure out exactly how long the trip that Halley's Comet has to take is. How far out does it need to go before it gets to the sun? So this is what we have of the picture of the universe as given to us by Kepler. And this leads us directly into Kepler's first law. So Kepler's first law specifically refers to... Oops. Kepler's first law. So, using the sun's gravity. I assume you're referring to this? If that's... yeah, that's right. Kepler's first law basically states that planets travel in elliptical orbits, or elliptical paths, around the sun with the sun at the center. This is annoying me. Sorry. And I wrote that wrong because I was getting distracted. With the sun at one focus of the ellipse. So what's a focus? Well, I guess I'll try to show you what a focus is. So let's take an ellipse. There's our ellipse, okay? So we're going to draw a line straight across the ellipse like this. Hopefully right through the center. There we go. And we're also going to draw another line in the opposite direction, perpendicular to that. That's going to come here. Looks like it's in the center. So that point in the middle, right, that would be the center of your ellipse, right? So what are the foci? So the focuses are, there's two of them, and I don't know where it would be for this one, but it might be somewhere like right around here for this side, and maybe like right over here for this side. Okay. Now we're gonna name some things here. I'm gonna call the distance here to be A, and the distance here to be B. Okay. And A is only going to be the distance between this point here and the end, okay? The letter A is what we call the semi-major axis of the ellipse. And then you could say that B is the semi-minor axis of the ellipse if you want to. Okay. Now, the distance, so okay, let's label some other things here. So this point right here is called the focus. Maybe call this focus 1, and call this one focus 2. So those are the foci. F1 is a focus of the ellipse. And now it's worthwhile to tell you some of the properties of these things so you can understand what it is. your planet is going to be traveling around here. So here's your planet. Right? The sun is going to be right at one of these foci here, right? So this is maybe where the sun is right here. The sun could be right here at this focus right here. So let's say we draw some lines to represent the sun, right? And then just say that's the sun right there, okay? We label it with an S. No, I'm not going to do that. But that's where the sun is, okay? There's nothing over here. The sun is right here. The planet travels along this elliptical path like this, right? Now, what the foci represent are the following. If I were to take a line, and I was to connect it from here to here, and then I take another line, and I connect it from, take another line, and I connect it from here to here. Like that. What the foci represent is that if I take the length of the line segment F1P plus PF1, or F2, sorry. If you add up this line segment here plus this line segment here, this number is a constant. Okay? That number is a constant. Okay? I wonder if I can do something here. I'm going to alter this diagram. I don't know how well this is going to work. I wonder if I can show you. It's not going to work. I thought it would work that way. Now, a circle is a special case of an ellipse. Okay? A circle is like a perfect ellipse, you might say. It's an ellipse where both of the foci in the circle are at the same location. You understand? And the arc, F1P, would then be basically just the radius of the circle. And PF1 would also be the radius of the circle. Can you guys see that? But then imagine, to create an ellipse, what you have to do is you have to basically take this center and pull it apart into two things, a foci and another foci. And what happens then is that the line drawn from there to there, and then P to F2, when you add those together, you get a constant value, okay? In the case of a circle, it would be double the radius. Does that make sense to you guys? So that basically defines what a focus is for the ellipse. And the sun's there, and the planet's there, and we travel around in a circle like this, okay? Now, there's another piece of this puzzle. This is where I wish I had my notes with me, because I might get this wrong. You notice in this diagram here, I hope you can see how this corresponds. It's probably easier to see how this corresponds to this picture, right? You got your comet, it's going around the sun's here. It's a really elongated thing, right? Orbit of Mercury, the sun's a little bit off center. Looks like a circle, but it's not a circle, it's an ellipse, right? But one thing it mentions here, it says the shape of the orbit of Mercury, which has the highest eccentricity, E equal to 0.21, among the 8 planets in the solar system. Okay? So what's eccentricity? I think I'm reasonably certain. I'm going to try this. I'm pretty sure this is right. I think if you take this distance here, I'll put it on this side because it's both sides the same. E times A is this distance here. E times A. So E is what we call the eccentricity of the ellipse. How eccentric is it? Okay? I'll give you some examples. EA is the distance basically from the center to one of the foci, and it's the same on both sides. This side would also be E times A, right? It's the distance between the focus and the center multiplied by the semi-major axis. So for example, if E, let's do the circle first, right? What would E be for the circle? It's 0, exactly. So that would be a perfectly circular orbit, right? A perfectly circular orbit would have an eccentricity of 1. This is the kind of thing you can go look up. You go Wikipedia Venus, and it's going to give you its eccentricity, right? It's one of the features you're going to see. You're going to see, like, its distance from the sun. You're going to see its mass. You're going to see maybe its atmospheric composition. And you're also going to see eccentricity of this orbit. It's going to be one of the astronomical features that you're going to want to know about something like that. So eccentricity, right? So now you can get an idea of what each of these things, like how this stuff works, right? So with Mercury, the eccentricity is 0.21, right? So that means that this distance between here and here is basically 20% of A, right? If E is 0.21, right? So for Venus, sorry, Mercury, my bad. Mercury, the eccentricity is 0.21. For Halley's Comet, and this is where I almost want to kind of like just pull up the internet and see what it is for Halley's Comet. No, we're going to calculate it. We don't need to do that. We can calculate it off the number of years that we know. But the eccentricity of Halley's Comet, I think I actually know what it is. I think off the top of my head, I'm pretty sure that the eccentricity for Halley's Comet, I think it's like 0.97. Something like that. Which would mean that, I mean, you can see in this picture it has to be close to 100%, right? Because the sun is here. You can see that the focus is basically almost on the edge of your ellipse, right? So that's why Halley's Comet has an eccentricity of 0.97. Maybe somebody can look that up real quick and tell me if that's right or wrong, or we can do the calculation pretty soon. I could just do the calculation. I don't want to teach you the math first before you do it. That's pretty close, 0.967. That's it's pretty good. Okay, thank you for putting that there, Nate. All right, now that's some stuff about ellipses that we need to know to do some calculations here in a little bit. So, all right. The other things we can mention about this is that while a circular orbit has an eccentricity of 0, and while a elliptical orbit has an eccentricity between basically 0 less than e less than 1, that corresponds to an ellipse, right? So this is the part about this is really cool. If you have e equal to 1, and you have e greater than 1, any idea what these might represent? Yep. This would be a hyperbolic path. We'll talk about what that looks like. And what would you guess in between ellipse and hyperbola? What does that have to be? There's only one conic section left, right? Yep. So the orbits of planets, asteroids, meteors, comets, everything in the universe follows one of the conic sections, basically. And that's kind of beautiful, right? So it's like the Greeks had it right, that it was one of the, that all the things in space basically followed some perfect mathematical idea, but they just picked the wrong one. They picked this one. And it's the special case. All the orbits are described here now. Conic sections. That's the paths of planets through space. That's the path of distant objects through space. That's the path of galaxies through space. Maybe the galaxy's part I'm going too far. But the stars within the galaxy, they travel along one of these possible paths. Inverse square law? We'll get there. So what's a parabolic path look like? A parabolic path would be like, suppose this is the sun, right? And I've got my distant object coming in from space, and it comes by the sun. The sun's gravity basically causes it to turn around, and it basically just goes off and never comes back. Right? It comes in this way. It's a no return path, right? It's kind of the kind of thing you want to do if you want to slingshot around a planet or something like that to get a boost of energy. Something else we'll talk about here in a little bit. So these things describe the type of paths that you can have, and depending on what the incoming velocity is right here, you either get, if it's too slow, it might get trapped by the sun. If it gets trapped by the sun, it's going to be an elliptical orbit. If it doesn't get trapped by the sun, if it has enough energy, it can escape the sun, and that means it would travel off to infinity on one of these paths right here until it interacts with some other nearby star or galaxy or planet, right? So that's Kepler's first law. Now, I have a table. I think we're too soon to go to the table now. Where is it? Real quick. Let me just find it real quick here. Does this have eccentricity? It doesn't. Okay, so we're a little ahead of ourselves on that. Just some information about the planets. All right, so that's Kepler's first law, okay? And there's a couple more. Let's do those next. Oops. So the second law works like this. We need another picture. We don't need nearly as many lines in it, though. All we need in this picture is the location of the focus, so here's the sun, and the location of our planet, so here's our planet. And then all we need to do is to draw a line, or a few lines, between this point and this point. So Kepler's second law states this. I'm going to say it in words, because maybe I'll write it, I'll type it out or something, but... Suppose that the planet is traveling along its elliptical path, and you draw a line from the sun to the planet, and then you look at where the planet is, let's say maybe this time period to go from here, let's call it 1 Earth month. Let's say it takes 1 month to go from there to there. And at this time, you draw a line, again, between the sun and the planet, and, okay, once you've done that, you realize that you create kind of an area in this regime here. So, like, in this region right here, you have basically some area, and let's say we call it A. And that's basically the area of this entire system right here. What Kepler's second law states is if it takes a month for the planet to go from here to here and it sweeps out some area that we call A, if we then wait 1 more month for the planet to, let's say, move to here, and then we draw another line, well, we're going to get a little bit of different shape. Oh, no. I have to use, like, lines for this because I just don't want it to look really crappy. So if you draw another month later, oops, click, same area, exactly. This is where I might need to adjust this just a little bit off my dot, because I think I made the dot a little too... Oh, it doesn't want me to do that. Nope, I didn't think it was going to work. Well, we're just going to fudge a little bit, or we can use the small eraser and just kind of do that. So, lost a little of our curve, but we can kind of go back in here and draw it in a little bit. And then now, our planet's here. But again, 1 month has passed. 1 month has passed. And now you get exactly the same area. The same area A here. So his second law states this. I'm just going to type it out. There you go. So it goes faster when it's close to the sun. That's exactly right. Okay, so I'm going to type out what it says. It says a line drawn from the sun to the planet sweeps out equal areas in equal times. Every month, that area swept out is the same. Such an interesting thing to say in reality, and also to have figured out for him. But the idea then is, if you start to think about what this means, if I want to get the same area, let's say over here, okay, if I want to get the same area for a line, I'm just going to draw this freehand now because I don't think this matters that much. In order to get that same area A on the other side, when you get closer to the sun, you need to make that little section a lot fatter, right? If you want to get the same area over here, you need to make that section quite a bit fatter, right? And that means, from a linear velocity perspective, that when the planet gets to this side over here, it's going to have to cover a lot more distance than it does over here, right? And then exactly as Bia said, that means that the velocity of the planet when it gets to this location is going to be much bigger than its velocity when it's over here. Slow, fast. Slow when it's far away, fast when it's close to the sun. And that's it. A line drawn from the sun to the planet sweeps out equal areas in equal times. It's fast on this side, it's slow on that side. That's all that it means. It means that the planet goes around and it basically goes really... Here, I'll use my arrow to say this. It goes really slowly out here. Slows down, slows down, slows down. And once it gets to this point, it's moving as slowly as it possibly can. This point out here is called the Aphelion. Okay, this point right here is called Aphelion. Or apoapsis. Specifically Helion because sun. You've heard of apogee. You've heard of perigee. That's when it's the Earth at the center for like a satellite or something like that, or the moon. This side over here is called Perihelion. So apo means far or away, and peri means near. So it's perihelion, or the more general term is periapsis if it's not the sun at the center. This is the close approach. This is the far approach. This is the farthest distance. And it's fast at perihelion, and it's slow at aphelion. That's it. It's fast at periapsis, it's slow at apoapsis. This is like the peak. It's like when you throw something up in the air, right? It goes up, and then it falls back down, right? And it hits the Earth. This describes what would have happened if the Earth wasn't there. It would go up to the top. This is like the apex. You've heard the word apex, right? The apex of the trajectory. This is like the top of the trajectory as it's falling around the Earth. That's what's happening here, by the way, is the planet is literally falling around the sun. It's falling towards the sun, and then as it passes by it, it kind of falls away, but then it comes back. And then it falls away, and it comes back. Just like when you throw something up in the air, it comes back down again. It's exactly the same process, right? It speeds up. Same thing happens here, right? The velocity of the object is 0 when it gets to the top of a trajectory like this, right? That doesn't exactly happen here. It's just slow. But you guys get the idea? So that's Kepler's second law. Now, we'll prove this once we introduce Newton's law of gravity, okay? We'll actually physically prove, using angular momentum, where this is coming from. It turns out that what this really says, another way of saying it in modern language, is angular momentum is conserved. That would be the modern way of saying this. Okay? Angular momentum is conserved. So we'll prove that here pretty soon. But finally, we need to talk about Kepler's third law. Any questions about the second law? It's kind of complicated. You need a picture. Things move fast when they get close to objects. They move slow when they're far away. That's pretty simple. All right, third law. So Kepler's third law specifically refers back to this picture now. And in particular, it refers to two things. One of them is the semi-major axis of our ellipse, A. Okay, remember that's basically the longest side cut in half. That's what A is. And Kepler's third law states that if I call the period of the orbit is represented by the symbol T, capital T, that's period. And what that means is the time for one orbit what is T for the Earth? Yeah, it's a year, basically, right? Or 365.25 days, as you said. It's the time for one complete orbit around the sun. Right? And then you know what the semi-major axis is, right? A is the semi-major axis, right? Again, just to remind you, on this picture here at least, if this is the center of your circle, then A is this distance, or of your ellipse, then A is basically this distance here. It's kind of like the radius, but it's not, because you're going to have two different radii, effectively, right? Because B is shorter and A is longer. So A is the semi-major axis, and what Kepler's third law states is this. It states that if I take the period squared, that it's proportional to the semi-major axis cubed. And this is where I want to grab the, what's it called? This. So we can actually look at how we figured this out. So this is a set of data regarding planetary bodies, okay? And this is the kind of data that Kepler would have had. He did not have this. He had no way of knowing at the time what the mass of the objects were. We will talk about how you calculate the mass of these planets pretty soon. But he had no way of knowing this, like the mass of the sun, the mass of the Earth. It wasn't until like about 1800 that anybody was able to measure the mass of the Earth. And that was a guy named Cavendish. So, but things he would have known would have been things like this. What is the symbol? This symbol means proportional to. means proportional to. It basically, another way to state this, it's not alpha, it's proportionality sum. Another way to state this is if I take the ratio of t squared divided by a cubed, okay, that this is equal to a constant. You take the period divided by the semi-major axis cubed, then you get a constant, basically. All right? We're going to do calculations with this, so it should become more clear what it is that we're doing. But so basically, you take the period right here, you square it, you divide by this, and then you get this right here. And you see that it's basically constant across all the bodies. Mercury, Venus, Earth, Mars, Jupiter, Saturn. He wouldn't have had these other ones, but there you go. It's a constant, basically. All right? So that is, yeah, that's I don't know what to say. That's Kepler's third law. That is Kepler's third law. Let's do a quick calculation with it. Now, there's something missing from here, and it's something that we're going to need to know something. We're going to have to use Newton to actually turn this into an equation. But if you want to turn something like this into an equation, basically you just say t squared is equal to a constant multiplied by a cubed. All right, so we could do something like, what could we do with this? We could, we need to know what the constant is, don't we? I guess we can see what it is right here. No. Yeah, the direction doesn't matter. It's just, this is equivalent to saying this, where k is not a variable, but k is constant. Just some constant. Proportionality constant. Yeah. So, I think we can do one of these problems really quickly here. I want to do at least one problem today, otherwise. I think we can do... Where is example 1? Oh, there it is. Let's use Kepler's third law to do a calculation so you guys can understand more about how it works. So the average distance between the Earth and the Sun is defined as 1 astronomical unit, 1 AU. And what is 1 AU? Well, 1 AU, you can see it on this thing right here. Where's Earth? Right here. That's 1 AU right there. So 1 AU, astronomical unit, is basically equal to, what is it, 1.5 times 10 to the 11. Whoops. Meters. That's 1 AU. It says the average distance between the Earth and the Sun is defined as 1 AU. The average distance between Jupiter and the Sun is 5.2 AU. Find the period of Jupiter's orbit in years. So, this problem is going to be really fast. I hope it'll help you understand how this works. So we have this relationship here, right? And when you have a proportionality statement like this, you can set up ratios. That's why we call it a proportionality, proportional. The ratio would look something like this. If I take the period of Earth, okay, and I square it, and I divide that by the period of Jupiter, this should be equal to the ratio of the semi-major axis of Earth cubed divided by the semi-major axis of Jupiter cubed. Does that make sense? So that's what that means, really, is I can set up ratios like this. Now, what do we know in this problem? Well, we know that the period of Earth, we're going to know the semi-major axis of Earth, and we're going to know the semi-major axis of Jupiter. The semi-major axis of Earth is 1 AU. The semi-major axis of Jupiter is 5.2 AU, astronomical units. And the period of Earth is the period of Earth around the Sun. So how long is this? What's the period of Earth's orbit around the Sun? 1 year, exactly. So that's the data that we need, okay? So what do? Well, we plug all our information in here and we solve for TJ, because that's what we're trying to find. Find the period of Jupiter's orbit. So let's solve for TJ here. This is what we're going to get. So TJ squared is going to be equal to right? And let's plug in the numbers. So we're going to have period of Jupiter is equal to, and actually let's do something else here. Let's square root both sides. If we square root both sides, that's what we're going to get, right? It's like raising each side to the 1/2 power. So we're going to have the semi-major axis of Jupiter is 5.2. We don't need to convert this, actually. It's one of the great things about proportionality statements. You don't really care what the units are. And then we multiply by the period of Earth, which is 1 year. So that ratio right there is basically going to tell you just how long Jupiter is. 11.9. So something like 11.9 or 12 years. And that's what Kepler's third law allows us to do. It's pretty neat. That you can relate the time that it takes to go around once to the distance. And now, knowing what you know now about physics in general, you start to think like, well, that's not chance, right? It's not like, I mean, this is a weird relationship, right? I mean, it's not complicated, but it's a weird relationship, right? Why would period squared be related to this distance cubed? Like, what does, where did this come from? Well, for Kepler, he was just pouring through data, and he saw that this was the relationship. Like, he had these numbers, and he's like, well, how does this number and this number compare? I think a really good thing for you to do, if I just, maybe I should do this in the future. I should just give people this data, these pieces of data right here, and then say, use Excel, and see if you can investigate the relationship between this column and this column. This is probably pretty hard, actually, to figure out that if you take this squared, it's equal to this cubed, right? It's not going to be simple. It's certainly not easy to see unless you're just really good at mathematics to see the pattern here, right? But he saw it, and this is Kepler's third law. I got to tell you, it's one of the things in physics. It's an old law, but it's one of the things in physics that we believe this. I would say so blindly that it's led to we really think this should be true. I don't know how else to put it. Like, we really believe that Kepler's third law is fundamental somehow to the way that the universe works. And unfortunately, it doesn't work. Whenever you talk about galaxies. We'll talk about that later. It works in our solar system really well. It does not work for galaxies. And we don't know why. We have no idea why. But we really, really believe that it should be true. I say we. I mean, I don't know if I'm part of it. Scientists, they really want it to be true. But once you go outside the solar system, it just doesn't work anymore. And we'll talk about why. So there you go. That's Kepler's third law. You guys have any questions? I think that means we can start talking about Newton then. Just making sure that this question isn't from a student. No. All right. So, yeah, that's it. That's Kepler's laws. That's 3 of them, right? Let's go back through them really quickly again. First law was elliptical orbits with the sun at the focus. The second law, fast when you're close, slow when you're far away, or you can, if you want to say it like that, you can. Or you want to say it like this, you can. Angular momentum is conserved. And then the third law, which is literally an equation that relates how fast to how far. Well, it could be this one too, right? Just depends on how you draw it. You know what I mean? Like you can flip it symmetrically around the center, right? So it's not super important. You know, yeah, it's at one of them, and there's nothing over here. There's nothing here. It's just the sun's over here. The planet travels on this path, and there's nothing at the other focus. It's just a mathematical object. Yep. What do you mean? It is similar to circular motion, yeah. It's a special case of circuit, yeah, that's right. I mean, what's making this happen is what we need Newton for, though, right? Understand that Kepler's laws are an observational fact about our solar system. He observed that this was true. He observed that this was true, and he observed that this was true, right? Observations teach us all these things. They're empirical laws, right? They're empirical laws. When I say empirical, I mean they are discovered through experimentation, observation, etc., right? They do not answer the question of, but how does this all work? Like, what is it that makes this thing do this? Where's the force, right? Where's the force that actually causes the planet to do this? Because we know that things in the universe, basically, they don't travel in circles. They travel in straight lines, right? They travel in straight lines. And in order for things to not travel in straight lines, you need a force. And the force is going to come from the sun. Now, Kepler himself investigated, you know, what it might be that was drawing this object towards the sun. And I think it was him that thought, and there were other people that thought, they knew about magnets, and they thought, well, maybe the sun's like magnetic, and it's attracting the Earth. That actually would work. If there was some kind of magnetic force of some kind between the sun and the Earth, that actually would explain what we see. So they knew that there was some kind of a force. It had to be an attractive force, but they didn't really know what it was. So, go ahead. Inertia. Yeah, inertia. So the Earth doesn't spiral into the sun because it's got inertia that carries it and keeps it in space, and it has no way to lose energy because there's no friction in space. If it could, if the Earth could slow down a little bit, it would start to spiral. Not spiral, but its orbit would decay. That's something I'm probably going to talk about next time by using Kerbal Space Program, so I can show you guys what happens when an object slows down in space and how it alters its orbit. But I guess what I would say is, like, we'll put it this way. Suppose that this is the Earth's orbit. The Earth has an eccentricity of like it's almost perfectly circular, by the way. So the Earth, we live in a very unique place in the universe, by the way, I would say. The eccentricity of Earth, can someone go look it up? For Earth, the eccentricity, and remember this is a number between 0 and 1, I think the eccentricity is like 0.021 or something like that. I think that's what it is. Can someone go look that up real quick? So, so here's the Earth. Okay, so it's 0.02, but it's not. It says 0.0167, they're saying. Okay, thank you. Appreciate that. It's pretty close, though, still. Alright, so here's the Earth, right? Now, the Earth is traveling around in space. It's traveling through space, traveling around the sun. It's going in a circle like this, right? And you're wondering, Ash, like, what is it that prevents the Earth from kind of falling in? And what I would say is, like, there's no forces on the Earth that can reduce its speed. So it's basically just traveling effectively with this uniform circular motion, and the force that's affecting it, which we're going to learn about now, is just the force of gravity, that the Earth is pulled towards the sun, right? And because these are at right angles to each other, the force of gravity doesn't change the speed, right? It only alters the direction of the velocity. Does that make sense, Ash? Now, if you were to put some rocket boosters on Earth, and you made it go faster, I'll show you what would happen. If you made Earth move more quickly, this is what would happen. I'm going to draw off. That's not a shape. Get my circle thing. This is what would happen. So if the Earth was moving faster, this is what would happen. I think that's good. If the Earth were to gain speed, its orbit would look like this. So if at that one location right there, the Earth got a boost of energy, this is what would happen. It wouldn't change how far away from the Earth it is on this side. it would change how far away from the sun it is on this side. Does that make sense? And what would happen if the Earth were to slow down? If the Earth were to slow down, something like this would happen. Okay, it wouldn't act, if the Earth slows down, the orbit would do something like that. It would become more elliptical, basically. So, spiraling into the sun, it would have to lose a lot of speed, actually. Okay, does that help to understand or answer your question at all, or? Okay, so let's talk about this force of gravity. So, Newton had the goal of uncovering the reason behind this idea right here, Kepler's third law. Okay, that's what his goal was. And he knew that he was going to have to produce a mathematical theory that described the force of gravity and the way that it works on a solar system scale. So what he knew was that things on Earth fall to the ground, right? And what he did was he connected the fact that things fall to the ground with what the moon was doing. He looked up at the moon. You know, the story is the apple fell on his head and he discovered gravity or whatever, but the truth is, he was thinking about the moon. He was thinking about an apple and realizing that they're the same thing. You know, the moon is made of the same stuff that the Earth is made out of, and why would it be made of anything else? So it certainly has to be affected by gravity just like the apple is. And he knew that he needed to create a force to make it work, right? He knew that if this is the moon out here, and this is the Earth down here, and the moon is going in roughly a circular path around the Earth, he knew the only way that would happen in physics is he needed to have what he referred to as a central force. And his question was, what would that central force be? What is it that's doing this? And the only force he really knew much about was gravity. And he thought, you know, maybe the moon is just falling around the Earth. Just like, you know, things fall towards the Earth all the time. Maybe the moon is just falling towards the Earth. And what he said was that this force of gravity, it basically, and here I can use the symbol again for you guys, he knew it had to be proportional to something. Okay? Now, he tried different things. He said, maybe the force is something that's proportional to the radius of this orbit, okay? And then he said, no, maybe it's proportional to 1 over the radius. Maybe it's proportional to the radius squared. Maybe it's proportional to the 1 over the radius squared. Maybe it's proportional to 1 over the square root of the radius. He tried, like, all these different possibilities. He's like, which one is it? The force, I know it's related to the distance. How do I know it's related to the distance? Because this equation tells me that it is, right? He knew that the distance had something to do with it because it shows up right there in that equation, right? The distance is related to the time. And distance and time, the way they relate to each other is they construct velocities, right? So he knew that this is tied together in this sense, and he knew it has to be something related to this, right? And he has this really beautiful passage in the Principia, which is his book where he discusses this, where he says, if we make it this, that leads, I think this is the one, this one leads to spirals. So he's just sitting around playing with mathematics, basically, in his office. It's like a 19-year-old savant. And he's like, well, if I make it proportional to the radius, I'm going to get spiral orbits, and that doesn't work, right? And if I make it proportional to 1 over r, I get some other kind of curve. But he figured out that this one in particular, this one led to orbits that are elliptical. And that was the key, right? By using this particular choice of the central force, it created orbits that were elliptical, circular, etc. And he knew this was true because that's Kepler's first law, right? This basically ties together, universal gravitation ties together the first law with the third law and the second law too, but more specifically, like, it allowed him to say, data tells me that this is how it works. Kepler tells me that this is how it works, so I've got to go with 1 over r squared. And that's where we came up with what's known as the inverse square law. You hear this expression a lot in physics, and this is maybe the first time you're encountering it in this class, but you probably encountered this. An inverse square law is something where the force, in this case the force of gravity, is proportional to 1 over the distance between the objects squared. Okay? So if this distance is r, the force between the moon and the Earth is proportional to 1 over r squared. Now, he knew it was proportional to some other things too, and in order to make this an equality sign, okay, you need to have some other things in here, okay? And what are those things? Well, they are the masses of the objects involved, okay, so one mass times the other mass, and you need to divide by r squared, okay, and then you need another constant right here. And what that constant is big G. This was his force of gravity. Now, he didn't calculate this, he knew it existed, and he actually did calculate it, I'm lying to you. He tried to calculate. He made some guesstimations, and he tried to calculate, and we'll talk about what those were. But this is his force of gravity, okay? It's an attractive force, okay? And the way it works is, if I take one object here and I call it mass 1, and I take another object here and I call it mass 2, the force of gravity is a force that exists between the two of them, and that force is equal and opposite on both bodies. It's an attractive force, and it depends on how far apart the objects are, and it depends on how heavy they are, okay? In our equation here, you've got mass times mass, so the bigger the bodies, the bigger the force of gravity is going to be. Large objects are going to create huge gravitational forces or pulls on things. This is where you go and you look at this table up here, and you start to think, wow, it must take a lot of mass if you want to hold together a whole solar system with just some kind of force. And you might notice that the mass of the sun is 10 to the 30, while the mass of, like, the Earth, for example, is 10 to the 24. Okay, and I know looking at tables like this can be hard to read, but all you need to know is that you could basically take 1,000,000 Earths, and they would equal the mass of the sun. Right? 1,000,000 Earths to equal the mass of the sun. The sun is 1,000,000 times more massive than the Earth. The sun accounts for something like 99.5% of all the mass of our solar system is the sun. Everything else is just negligible, you know what I mean? And, yeah, so that's Newton's force of gravity. It's an inverse square law, and we have a proportionality constant G. This was measured more specifically by a guy named Cavendish, and it's equal to 6.67 times 10 to the minus 11 Newton meters squared divided by kg squared. And that's Newton's law of universal gravitation. Do you guys have any questions? I see someone typing, so I'm just waiting to answer. You know, people in Newton's time, while you're writing, I'll just mention that people in Newton's time, they found this to be spooky. They used this spooky. If Cavendish found the G, did Newton not have that calculation when he found Fg? Yeah, that's right. That's right. Yep. So what Newton did was, to be more clear, Newton approximated the value of this by making an assumption about the density of the Earth. So let's there's tons of things I can say about this equation, okay? But let's do something really, really simple real quick here. Let's talk about this. So here's the Earth, right? And let me go down a little bit. And like, let's say there's a person right here, and they jump off the surface of the Earth, right? And I say this person has a mass m1, and I say the Earth has a mass that we call m2, and the center of the Earth is down here. And then the distance between these two objects, oops, sorry about that. The distance between the person and the center of the Earth will be this distance right here. It's basically just the radius of the Earth at that point, right? Which is about 6 times 10 to the 24. Wait, no. 6.4 times 10 to the 6, my bad. It's 6,400 kilometers. I hate it when it does that. 6400 km. I think that's the easier way to remember it, because kilometers is easier to remember. So let's think about what's happening to this person. Now, I told you guys before, if I was to ask, this person jumps off the surface of the planet, what forces are acting on this person? It's gravity, right? Or it's weight, right? Well, now we'll say the force that's acting on this person is the force F sub g. And if this person has a mass m1, we would say that that force, right, is just equal to big G times m1 times the mass of the Earth divided by the radius of the Earth squared, right? But we also know that when someone jumps off the surface of the Earth, they have an acceleration, right? In this case, they have an acceleration that points down this way, and that acceleration is equal to gravity, right? So we can say, oh, well, I know net force acting on my object then, my person, is equal to the mass of my object, which is what, m1, right? Times its acceleration. The left-hand side of the equation just becomes Fg. The only force acting on the person is Fg, right? So you do G, m1, m2, and you divide by the radius of the Earth squared now. And then this ends up being equal to the mass multiplied by the acceleration, but in this case the acceleration is just the acceleration due to gravity. And then you notice that the masses of the person actually cancels, and lo and behold, we've actually proved that the acceleration due to gravity near the surface of the Earth is a constant. Where now, the mass, m2, is just the mass of the Earth, right? And we can do a little bit of a calculation here. Oh, squared. We can do a calculation here. We can actually plug the numbers in and see what we get, right? So let's use some values. So m2 is given in this table that I linked just a second ago. The mass of Earth is 5.97 times 10 to the 24. Okay, we're going to use as much accurate as we can here. 5.97 times 10 to the 24 kg. And then we also know the value of the radius of the Earth from that same table. The radius of the Earth is 6.37 times 10 to the 6th. So that's an approximation. So it's 6.37 times 10 to the 6th meters. And then you've got G over here, right? You can plug all those into this equation right here to get an answer. Now what I'm going to do is I'm probably just going to pull this up on a calculator. I don't really enjoy writing scientific notation into... okay, I don't want that one. I want the other... Do I have another one open? No, I don't. So we'll pull on the online scientific calculator. And this is something where... Here, I'm going to do it both ways, because it's really important that you guys get good at this, especially... So what is this equation going to look like now? It's going to be 6.67 times 10 to the negative 11. And then we multiply this by mass. So that's the mass right there, 5.97 times 10 to the 24 kilograms. It loves doing that on my fours. Just loves it. 24 kg. And then we divide by... Can you guys do that calculation for me? So this is the thing. When you type this into your TI, you're going to be typing something like this. Except with the TI, you're going to have like a capital E. There's a little button you can push. I highly encourage you to use the scientific notation features on your calculator. You do not want to put 6.67 times 10 to the negative 11 like this. It's really easy to make mistakes when you do this. You have to use a lot of parentheses and stuff like that. Instead, if you just use the symbol on your calculator, it looks like this, right? On your calculator, on whatever calculator you're using, there's some symbol that looks like this. And no, I don't mean the times 10 to the whatever. I mean this button specifically. On this calculator, it's just a little e. So I put 6.67, and then you do minus 11, and then times 5.97 times 10 to the 24. And we divide by 6 point... This is where you can avoid using, like, parentheses if you do this. And then you do like that. Notice that I put this entire equation. It's not, though. On this, it's both. On this calculator, it's both, by the way. So you plug those in like that, and you get 9.81, right? As you guys are saying. It's exactly what your book tells you, and if you did measurements, what the acceleration due to gravity on Earth is, right? You end up getting G is equal to 9.81, and if you check the units, you're going to get meters per second squared, right? So that's where that number comes from. I mean, you can measure this, right? So now think about like this. How, okay, I want you guys to think about this. How could Newton have tried to figure out what G would be? He doesn't know what it is. Newton couldn't have done this calculation. but he would have known this number. Newton would have known what the acceleration due to gravity is on Earth, 32 feet per second squared, right? He also definitely knew this value, okay? He definitely knew what the radius of the Earth is. This has been known for, like, since ancient Egyptians, like, way before. I mean, it's very easy to use, like, a stick in the sand with looking at its shadow to determine what the radius of the Earth is, okay? As long as you put the stick in the sand at 2 different locations and you know how far apart they are. So this was also something he knew, right? So when you look at the equation, he basically was missing 2 pieces of information, right? And he would need a second equation, some other kind of piece of information to solve for one of them, right? He doesn't know these 2 values. He did not know the mass of the Earth. He did not know what g was. It was just some kind of constant. He didn't know what it was. Oh my god. What on earth is that? It's kind of artifact. What do you guys think he did? Any ideas? No. Galileo already did that. Galileo came before Newton and understood exactly this. Dimensional analysis, nope, it wasn't that. Dimensional analysis can give you an idea of what the equation is. It can't tell you the values, though. It's a good guess, though. mv squared over r. Nope, he didn't use centripetal force, although we are going to use that to prove where Kepler's first law comes from, or third law, sorry. I'll tell you this. He had to make an assumption about the Earth, basically. You want to take a guess at what he did? I'll tell you this much. He knows what the volume of the Earth is, too, right? You guys see that? If you know the radius... Yep. He's... Well, what would he need? What piece of information would he need? Density. Via said it, that's right. He basically made a guess as to what the density of the Earth was. He didn't know, but he said, the Earth is made of a lot of water, and it's made of a lot of rocks, so he basically took the average density between the 2 of them, between the density of rock and the density of water, and he just said, let's use that and plug it in here. And then he used that to roughly approximate what g was. And I think he got something like 4 times 10 to the negative 11, which is pretty good, actually, if you think about it. But it wasn't until Cavendish used something known as the Cavendish Balance, which we actually have at the school. Our school has one of these, and I can't even show it to you. It's so sad. But he used this thing called a Cavendish Balance to approximate g, and what Cavendish was actually able to do was to weigh the world. And once he could do that, he could also know the mass of the sun. And just think about how powerful knowing this constant is. It allows you to measure the mass of things that we can never put on a scale. There's no way you could ever measure the mass of the Earth the same way you measure, the mass of your, like, chemistry sample or something like that, right? There's no scale in the universe that's big enough to weigh a planet. But if you know this constant, and you know some data about the way things orbit, all of a sudden now you can find the mass of the sun, the mass of Venus, Can you imagine how powerful that must have felt for this person? That, like, all of a sudden, by a very careful measurement of this, something, his experiment, we haven't even improved upon it, by the way. Like, we still do his same experiment to this day to get an approximation for what g is, right? Is that the one he did in a shack and observed outside? I don't know. Maybe? Yeah. You may be right. I guess we could go... Is that right? What do you guys know about it? Cam, go ahead. Oh, that's awesome. Oh, that's so cool. I love that. I did not know that, and that makes me really happy. He was afraid that his own mass would alter it. That's great. All right. So, there we go. That's gravity. And Cavendish used this idea to measure the mass of all the planets and the Earth, and it's just extremely powerful to be able to know that kind of information about masses. So that's Newton's theory of gravity. Now, you mentioned mv squared over r, and I think the next thing we'll do is we'll basically just we're going to prove where this comes from. We're going to prove Kepler's third law next. Okay. Yeah, when we're able to go back to school, go into the 1A room and ask a teacher to show you how the Cavendish balance works. I mean, I can pull a picture up of it, but it's... Alright, okay. I need, like, a quick break. I need, like, a 2-minute break. Is that okay with you guys? I just need to walk away for 2 minutes. Is that okay with you guys? I'll start again at 4:33. So, next thing we want to do, as I said, is we want to prove... Oops. Proving. I don't know if proving is the right word. Verifying might be a better word for it. I don't know. So here's what we do. We take a really, really simple system, okay? We take a body. Let's just use the Earth is fine. And orbiting this body, we were going to place a satellite. This satellite is going to travel in a circular path. There's no reason not to actually just use a circle for this. I need to start getting better at this. I need to start using the tools that we have here. So you have a body that's traveling in a circular path around the Earth. It could be some kind of satellite or something like that. It could be like a satellite that provides, I don't know, internet or direct TV or whatever. It's just a satellite. It's orbiting around the Earth, right? And we say that the distance between the satellite and the Earth is r. We say that it's a circular orbit. So we don't have to worry about the elliptical part of it. And we say, okay, if this satellite has a mass and we call it m, and we say that the Earth has a mass that we call just me. Oops. Me. Then we can state that there's a force acting on our satellite that goes towards the center. It's the force of gravity, okay? And if at a moment in time our satellite has a velocity, and the velocity is going like this, oh, I thought I switched to green. There we go. If the velocity vector at a moment in time is going like this, right? Then we can relate all of these quantities to each other, okay? So v is the velocity, r is the radius, masses, etc. We've got all the things we need, right? And we can say that the relationship between all these quantities is going to be, if I sum up all the forces acting on my object in what I'd call the radial direction, that should be equal to the mass of the object times the radial acceleration. Now, what direction is the acceleration? It's toward the center, right? This object has a radial acceleration. Oh my god, that's awful because I'm trying to write so small. So it has a radial acceleration that goes towards the center, right? And what that is velocity of the object squared divided by the radius of the path. The force acting on the object is basically just g times the mass of the satellite times the mass of Earth, right, divided by the orbital radius squared. Okay? You can see the masses cancel out on both sides. And one of the radii cancel. And this actually leads to something that's pretty useful. The velocity in this case is basically equal to the square root of the gravitational constant multiplied by the mass of the body that's being orbited divided by the radius, and you take the square root of all of that. This is basically the velocity of a circular orbit. The velocity of an object in a circular orbit is given by this. But what are we trying to do? Well, we're trying to prove the t squared proportional to the semi-major axis cubed equation. Alright? And to do that, we need to talk about the period. So to get period out of this, we say that the velocity of our object is related to the period because the entire orbit has a path that's the circumference of a circle that has a radius 2 pi r, or has a circumference 2 pi r, and if we divide that by the period t, that'll give us the velocity, right? You take the path, you divide by the time around the path, that gives you the velocity, right? Distance over time is velocity, basically. So that allows us to replace our velocity in our equation here with that, right? So here's what we're going to do. For velocity, we'll replace this with 2 pi r divided by t, but then we need to square it and say that that's equal to, sorry, I didn't mean to change the r to a capital R, my bad. This should still be little r. And that's equal to the right-hand side here, which is basically g times the mass of the Earth divided by the radius of the path. And now we can start moving things around. So what we end up getting is 4 pi squared r squared over t squared is equal to. And now we can move things around. Move the t squared to the right. The r cubed will show up over here. And I think I want to put this, here's how it's going to come down. It's going to end up being r cubed is equal to t squared multiplied by just every time I draw a 4 pi squared period squared radius cubed, and then that's the constant. The constant is basically, you know, Kepler's third law basically says t squared is equal to k times a cubed, where k is equal to g m over 4 pi squared, where m is the mass of the body at the center. Did I get that right? This should be on your packet at the top of... It might be really the opposite way. Yeah, it's really the opposite way. It's still the same idea. So there you go. That's Kepler's third law and where it comes from. You guys have any questions? Did I do the math wrong? I could have made a mistake. No? Nope. You could replace... it's the m right here, in this case, basically represents the body at the center. The body, not at the center, but the body, yeah, at the body being orbited, you might say. So in the case of, like, we take the sun and we take the Earth, right, then in this case, your K for the sun would be G mass sun over 4 pi squared. So there you go. If you replace the sun with the black hole at the center of our galaxy, it'd be the same thing. 2 pi r. Oh. The r in this case is going to be the distance between the sun and the Earth. I don't know. Sorry, oh. Yeah. Circumference would be the same. Not the same value, because the distance between the Earth and a satellite might not be the same as, you know, the distance between the sun and the Earth. So that's Kepler's third law. This is pretty useful, actually. This is probably more useful for some of the problems we're going to do. But they're both useful for different reasons. You need all of these equations, basically, if you want to solve a lot of these problems we're going to look at. So it's 4:41, and I need to think about what I want to do the last 20 minutes of class. There's like a lot of options here. We can, like, I want to do this problem. The problem is we can't do it until I teach you about energy. So maybe we just do the energy stuff and get the theory out of the way, and then we can do all the problems. Because we can't do any of the fun problems. We can do this problem. I don't really like it very much. But, oh no, what did I just do? I don't know. You know, something I want... Oh, that's what I want to talk about. I was talking about it, then I just, like, lost track of mine. I want to talk about this equation in general. Where did it go? Newton's below this. My bad. This one. I want to talk about this equation. And this picture here. I don't know if you guys remember this, but at the beginning of class, like the first day of class, I want to say, we talked about types of forces. And we talked about contact forces and field forces, right? Contact forces are things like tension, friction, normal force, things that you touch. Weight is a field force. Gravity is a field force. And it's a field force because it acts over a long distance. As far as we know, the range on gravity is infinite. Like, there's no limit on how far apart things can be before they feel each other's gravity, so to speak. Things that are closer together, though, have stronger gravity, right? And usually you can ignore distant objects when you make gravitational calculations, especially if they're small. Yeah, I wanted to mention that, but I also want to mention that this type of idea, that gravity is a force that acts over some distance, I guess people thought was kind of spooky. They called this spooky action at a distance. It's like, what's making this happen? Like, why is it that this massive object here and this massive object here somehow know they kind of know where the other one is, right? Like, they don't know it because they're like inanimate objects, but like they kind of know, right? This body over here needs to know how far away this body is over here in order to understand how hard to pull on it effectively. Now, this isn't how things really work. They're inanimate objects. They're not thinking, right? But my point is, somehow, these two objects know the other one's there, in the sense that they feel this force between the two of them, and the force goes according to these rules, right? But like, where that comes from and why that might happen, they're questions that we can't really answer as physicists in a way. I mean, physics doesn't try to answer the question why, it tries to answer the question how, but nonetheless, it's often, you sit back and you look at these things and you're like, this is just so weird, right? Like, how can it be that this mass and this mass attract each other? It's completely, I want you to understand, it's completely and like opposite to the way we think about things in the world, right? You take two objects, like two balls, and you hold them. You don't feel a force pulling them together, but it's there. It's just incredibly weak. You take two magnets, right? And you can either see the magnets repel each other when you put the same poles, or if you put opposite poles, you'll feel the attraction between the two of them. The force of gravity is an attractive force in that sense. But like, apparently it's happening because of mass? You can see the demo with a tight fabric and you drop two different size balls and see how they behave for this topic. Yeah, are you talking about like how you can visualize gravity with like a sheet that's held tight and then like that's what you're talking about? Yeah. We'll get there. Yeah, we'll get there. We have a nice demo at school for that actually too. But that's general relativity. That's Einstein's gravity. It's not this gravity. We will get there though. So, yeah, like, do you guys see what I mean? It's just really weird. It's a really weird force. It's based on what? Well, when you say it, what do you mean exactly? Yeah. As far as we know, yes, is the answer to that question. And we've basically measured the speed of gravity, so to speak, with the measurement of gravitational waves. So we know that it moves, or like, at least the information about location travels at the speed of light, something like that. All right, so okay, Kepler's third law. We did the derivation here. We did the problem relating Jupiter, so you can understand how you actually, use the equation. I mean, I guess we do the billiard ball problem. Just such a silly problem. It's good though. It's really, really good for preparing you guys for 1C too. So that's like why I have it here. Let's do it. This problem is kind of boring. I promise you next time we're going to talk about energy, and we'll do some really neat things. But sometimes you just gotta do a problem that's kind of boring just to teach something. If you make it too complex, unfortunately, it gets really hard to learn from. But this is the problem. So 3 0.3 kilogram billiard balls are placed on a table at the corners of a right triangle as shown. So you have 3 billiard balls here, here, and here. Okay, and they're sitting on a table. They're not moving. The sides of the triangle have lengths 0.4, 0.3, and 0.5. Sorry, I'm yawning. Calculate the gravitational force vector on the cue ball, designated as M1, resulting from the two balls, as well as the magnitude and direction of this force. This picture already has some lines on here that I would not wanted to draw, but basically, you've got your cue ball. It feels a force that goes to the right from ball 3. It feels a force that goes up from ball 2, right? This ball is attracted to ball 2. This ball is attracted to ball 3. And we want to find the net force due to the other two, just on ball 1. To be clear, this ball right here feels a force this way, and it also feels a force this way, and this ball feels a force this way, and it feels a force this way, okay? But those are not what we're worried about in this problem, okay? We're only focusing on the forces on... No! Why is it doing this? Why must it do this right now? Okay, wait, is it gonna let me? Okay, I guess so. So we're only worried about the forces on this ball right here, ball 1. Okay? And what we know is we're basically going to be using I feel like I'm doing something wrong. It has to be, right? This happens so frequently. No! Why is it doing this? I can't believe I have to do this. Alright, there we go. Alright, so let's solve this problem. So F21. That's the force of gravity between ball 1 and ball 2. So it's going to be proportional or equal to mass 1 times mass 2. You need to divide by the distance between the two of them, a squared, and then you need to multiply by the gravitational constant g. Now we have the values of these things right here. So like a is equal to 0.4. What's the other value? We're going to need b, which is equal to 0.3. Am I recording? What's going on? What's up, Jose? Am I not recording? You guys can hear me, right? Okay. Alright, so b is equal to 0.3. For YouTube? Yeah, I'm recording this for YouTube. It'll be up. Okay. No, you're good. The videos don't go up until the end of class anyway, because I have to like process them and stuff. So we have these values. We know what g is equal to. G is equal to 6.67 times 10 to the negative 11. By the way, this number, it's not just true for Earth or our solar system or even our galaxy. As far as we know, g is a universal constant. It's the same everywhere in the universe, okay? We're pretty confident that that is a universal constant. But as we will learn, there's some problems with gravity. It's one of the biggest problems in physics right now. So this is the universal gravitational constant, and then what else do we have? We've got mass 1 is... Oh, they're all the same. So mass 1 is equal to mass 2 is equal to mass 3. That's nice. Everything is going to have the same mass. So 0.3 kilograms. So if we plug all those numbers in to our calculator... whoops. So that's the equation we're doing, right? And I'll make it smaller so I can get more things on the screen. So we have g. So g is going to be 6.67 times 10 to the negative 11. That's not what I wanted to push. Times 10. I'm just going to type it. 6.67 times 11 times the mass, so 0.3 times 0.3. And then we divide by a squared, so divided by 0.4 squared. Did the stream just cut out? I don't know. I hope not. Oh no. Yep, it's back. Good. So you get 3.75. That's the force we get by plugging in all this. Notice this is a really tiny force, right? That means that this force is utterly negligible, basically. The force F31, which would be the force from this ball, is going to be big G again, M1, now times M3, divided by B squared. So the answer is going to be basically the same, except we're going to need to multiply by, or divide by 0.3. So we can do basically the same calculation we just did, except we just change this to a 3, and we get 6.67 times 10 to the negative 11 newtons. And then, if I want to find the angle theta, you can say that basically the force 3, 1 points in the x direction and force 2, 1 points in the y direction. So if I want to find the total force acting on this object, I'm going to have to take the square root, I have to basically vector add these things. So F21 squared plus F31 squared, because they're at right angles to each other. And what that's going to be equal to is... so it's going to be 3.75 squared plus 6.67 squared, and then we raise that to the half power. So you get 7.65. And of course we can find the angle too, right? The angle is going to be the arctan of what? F21 over F31. And you guys can obviously calculate that if you want to, or we can do it real quick here. So it's 2-1 is, so it's this one over this one. So it's a tan of 3.75 divided by 6.67. 29 degrees, or 0.5 radians. Okay. So that's a field force problem. This is the kind of problem, like I know you have like maybe one of these on your homework, but it's the kind of problem that will show up in Physics 1C, like on the first exam. Okay, so don't brush this problem aside because it's just stupid. It is a stupid problem. You're calculating the force between billiard balls. Like, these forces are incredibly tiny. But it's kind of done to prove a point, that the force between normal objects with regard to gravity is tiny, right? To have any gravity at all, you need to have a huge mass to counterbalance this term. This thing is so tiny that you need to have a mass that's on the order of, like, well, a planet to have any effect on gravity, right? And that's why only large objects can hold, you know, matter on their surface. You have a very tiny celestial body, like let's say a small moon or an asteroid or something like that. If the mass isn't big enough, it doesn't have any gravity. You know, it's going to have very, very small gravity. That's why the moon has a gravitational acceleration that's about 1/6 the size of Earth's. Because, well, what goes into it? This. That's where the gravitational acceleration of a planet comes from. It's related to the mass of the planet, that's really important, and then it's related to the radius of the planet. Now, mass and radius are not necessarily independent of each other either, right? Because the bigger the mass, the bigger the radius needs to be, right? They're inherently tied to each other. In fact, if you want to remove one of these two from the equation, you could just put density in here. Replace the mass with, you know, 4/3 pi r cubed times the density, and, you know, you'd see what, like, how it would work out. But my point is that, like, because G is so small, any object that's smaller than the Earth is going to have a smaller gravitational acceleration, especially if it's also, you know, like, got a big radius. Okay, so we do this problem. Keep in mind that stuff like this will show up in Physics 1C, like, from the first day you take the class, basically. You know? You're going to have problems, and instead of masses, what you're going to have is charges. Electrical charges. And I heavily encourage you, if you have any questions about what I just did here, now is a great time to ask. Because the way that electricity works, it's almost exactly the same. Almost exactly the same as what we just did here. Okay, you guys have any questions? This problem's not hard, right? Would you guys agree with that statement? And maybe it's new to you and you don't understand something, that's okay. But it's pretty simple, right? Okay, good. Just remember that, because when you get to 1C and you're lost, remember that it's not that hard, I promise. It's you will be overwhelmed and it will seem hard, but it all comes back to what we just did. Everything in Physics 1c starts with what we just talked about. Like, it all begins with this. And understanding how to do what we just did. So, just keep that in mind. Everyone says Physics 1c is such a hard class. Most of it just comes because, I don't know, people get confused. Anyway, I think I'm going to stop this recording now and start uploading to YouTube, as that's officially the end, but I will kind of stick around and tell you guys some things at the end of class. So, I'll see you guys that are on YouTube in 2 days.